I'm delighted to introduce the NeoNext team, which is Pedro Santos, Head of Data Science for NeoNext Plus Energy, and Daniel Makoda, Senior Pipeline Engineer for NeoNext Plus Energy. And they're going to be presenting just before our lunch on AI-powered pipeline free span detection. I'm really excited about that. Over to you guys, and big round of applause. Thank you.
Morning. Yeah, my name is Daniel Mercado. I'm going to be presenting with Pedro a project that we developed in 2025 for the automatic detection of free spans on subsea pipelines from bathymetry data. So how many pipeline engineers do we have in the room? Okay. So my function then is going to be to explain every word of what I just said. Yeah. So it's a project for the automatic detection of free spans on subsea pipelines from bathymetry data. So, okay, we've got a little bit of an agenda in there. I'm going to go straight because I've got very limited time. So, engineering background. What is a free span and why do we get excited about that? Yeah, it's, as you can see in there in that little picture, you've got your pipeline sitting on the seabed, yeah? And what happens is that nature doesn't cooperate. You're going to have a scouring under the pipeline to the point that you've got empty spaces where the pipeline is not supported. Why do we get excited about that? Because the pipeline is designed to be supported. So when you've got a pipeline like that with holes under it, you're going to have two problems. Stress, because it's supposed to be supported and it's not supported anymore, and you're going to have fatigue. And the fatigue failure is the most important one in this case because of the catastrophic nature of the failure when it happens, yeah? So, yeah. I try to put quite a lot of pictures in my, and I'm going to try to go through the keywords, okay? So the important part in here is that the pipeline is going to suffer from stress and fatigue due to the fact that you have a hole under it, yeah? Now, the fatigue failure is the one that I want to focus on. And the reason is, I heard quite a lot of people talking about corrosion. When you are talking about corrosion, corrosion is gradual, yeah? It doesn't happen like this. You know, if you go and inspect it, you're going to see that there is a little bit of corrosion, and it's growing and growing and growing. And you can calculate a corrosion rate. And you can actually estimate how to mitigate and how to inspect it based on that corrosion rate. Fatigue, you cannot do that. It goes like this. You can go and see it today, half an hour later, failed, okay? Now, fatigue, in this case, is produced by something called vortex-induced vibration. If you have an object that is submerged on a liquid or a fluid, what is going to happen is you've got something called the limit layer. That limit layer, in this case, comes from the current, yeah? You have flow, you've got water going under and above the pipeline. You've got that limit layer, and that limit layer at some point separates. And as it separates, it creates vortices. Now, in nature, those vortices sometimes separate at the same time, and sometimes they alternate. Every time that you have the separation of a vortex, you're going to have a differential pressure. So basically, you've got your pipeline, and your pipeline is actually pushed laterally or cross-flow. What happens in nature, in reality, is something like this. So the pipeline is moving because the flow is going through it, yeah? And as the pipeline is moving, then you've got the potential for fatigue, okay? Now, what is fatigue? Fatigue is the localized structural damage that occurs when a material is subjected to cyclic loading. So in that picture, as you can see, that's a typical fatigue failure. It just goes, you know, as if it was very, very fragile material, okay? And the problem with fatigue is that, in general, when you're designing, you are considering the maximum tensile strength of the material, okay? When you are failing because of fatigue, let's say that you have 300 megapascals of strength. That's how you design your pipeline. When it fails because of fatigue, it fails at 100 megapascals. You know, very, very lower level of strength for that specific damage mechanism. So what happens, or what we need to do as engineers, is that we need to do a fatigue assessment. And the fatigue assessment is that chart that I put in there. It basically, in y-axis, you've got your stress, let's call it load for easy way to describe it. And in the x-axis, you've got the number of cycles. So depending on the load, you're going to have less or more cycles before you fail. The important thing in this is that when you do the assessment, what you're going to get is a remaining life. So basically, you've got a free span, you've got an anomalous free span, and I'm going to explain what anomalous is. You've got free spans, you do the fatigue assessment, and the result from the fatigue assessment is this free span has 4 years remaining life. Meaning, before 4 years, you should be mitigating that thing, or it will fail. All right? Providing that the conditions continue being the same conditions. Okay? Okay. How do we inspect for free spans? Well, in general, you can do ROV, world-class ROV, the 3 cameras, one on top, each side, and the laser and all of that stuff. You can also do SSS or multi-beam echo sonder, okay? The reality is, as a pipeline engineer, is that sometimes you've got 3 cameras and you cannot see where the span starts, where it ends, or if you have any intermediate touchdown point. It's quite hard to actually, not for all of them, but for the critical ones in general, it's pretty difficult. Now, when you're designing a pipeline, you calculate an allowable free span, okay? If you have a, I don't know, 24 inches pipeline and you have a little 1 meter span, that's not a problem, you know? But if you have a 40 meters span, that could lead to fatigue, okay? So your design documentation is gonna come telling you your allowable free span is 40 meters. If you've got a span longer than 40 meters, then you have an anomalous span, meaning you need to do the assessment, meaning you need to calculate what the remaining life of that feature is. Is that clear? So, inspection techniques, that one that you can see in there is multi-beam echo sonder, which is basically a sonar. You emit some ultrasonics, bounce from the seabed on the pipeline, and come back to you. You have another sensor, and you can create a map like that. So as you can see, there is not going to be that easy to see if you have an intermediate touchdown point. You know, it might be that you have a 36 meters span reported, but right in the middle or somewhere else, the seabed changes, and you have a touchdown point, and the span wouldn't be anomalous. And it's not that easy to see. And as I said, it's not even easy to see it from cameras sometimes. Now, this is where the thing is interesting, or I'm going to start talking now about the value proposition of this project. Yeah? So we have a free span integrity management process. So I'm going to go through this one by one. So first of all, you have an inspection. There is a person that is qualified to do that inspection. It's a surveyor. That surveyor's got experience on this. Okay, the guy has have a look at the data and says, yeah, the span starts here, ends here, reported, this is anomalous, this is not, yeah? Then that comes to the integrity engineer or the pipeline engineer. And that person will, depending on the data he's got, analyze if he actually believes that that free span is that length and all of that. So 2 steps, the very first 2 steps are 100% visual, okay? It's just you or the surveyor looking at the data. So little bit of a human error introduction in here. Then for the anomalous spans, you go and do a fatigue assessment. Yeah, that's the third step. And then that one that I highlighted in there is quite important because let's say, for example, that I've got an anomalous span and it tells me you've got 3 years of remaining life. The very first thing I'm going to do, I'm going to go for my previous inspection data that was, for example, 3 years ago. And I'm going to try to see if that span was in there 3 years ago with the same dimensions. Because if now you are telling me that my remaining life is 3 years and I had it there 3 years ago, that means that's about to fail. Yeah? So I take the decision at that stage depending on the previous history and the quality of the data that I've got. Okay? Then for the selected anomalous spans, I will plan for mitigations. Yeah? If I find myself in that situation where I have a span 3 years ago was there, I've got 3 years remaining life, I need to go and mitigate. Yeah? And the last step, obviously, is mitigating the span. How do we mitigate spans? We go there, throw rocks at them, okay? We do engineering to calculate the amount of rock, the size of the rocks, but basically it is just that. You hire a boat full of stones and go there and mitigate by covering that free span with stones. The engineering is because obviously you don't want to dent your pipeline, and obviously you need as well to consider if there are interactions between spans and all of that stuff. But, you know, it's a boat, you do engineering, and then you cover that area with stones. Pretty expensive operation, yeah? I mean, a spread in the North Sea for a boat, normal boat, DSB or ROVSB, is north of 100,000 a day, yeah? So if you can save this money, it's good for the business. And that is our value proposition. Now, let's say again, if I take you back for a second to that comparison of spans, yeah? If I don't have data to show me what happened 3 years ago or 5 years ago, or my data quality was not that great, or, you know, the seabed was quite, you know, dirty and moving and all of that, I'm not going to be able to actually compare what was happening, and I'm going to have to be conservative and go and mitigate stuff that maybe I don't need to mitigate. So what we're proposing in here, what Project achieved, is the possibility to detect the spans automatically, yeah, using machine learning that Pedro will explain, and then you've got the possibility to do that for a different set of inspections on the same pipeline, and you are able to compare what's going on, how your spans are evolving. It could be, if you see the one in August 2023, there is a red one in there. That one would be anomalous, okay? So if you see that one and then you see it in 2024, it went from red to amber. And in September 24, it went to amber from nothing. From amber to nothing, I'm sorry. What's that telling me is that the seabed is mobile. Seabed's moving, yeah? And then at some point I had a feature in there that it was, you know, using my remaining life, but as the span reduces, it changes, and then it's not affecting the pipeline so much. So much that it can even disappear. You could be in a situation where you detect a free span, you do the assessment, you plan for mitigation, you do all the stuff, and when you go there and try to mitigate it, the span's not there. And you spend all of that money and engineering and time. And you could be in an ideal situation where you have so much history that you can demonstrate to me that the seabed is mobile and no free span is going to really cause fatigue failure, because it will always be changing, okay? And I personally would say, well, let's not inspect for free spans anymore. We don't need it. Even if we find them, it's not going to be an issue. I think that's me, no? Yeah, and the last slide is just comparing between the manual process and automatic process to detect the free spans. But I think that you're going to be more entertained by Pedro. Yeah. Thank you.
Right, I'm very, very aware that I'm the thing between you and lunch, so I will be quick. What you're about to see is good old machine learning, so nothing to do with Gen AI, and with physics, which gets even better. So, because I have 6 minutes, we have the full team here today, and they have the names on the screen on the first and the last slide. So feel free to be involved. They know the full detail, so full credit to them. So starting from the start, so the data. So as Dan was explaining, each survey produces 3D point clouds. So this is effectively XYZ data if you want eastern, northern, and depth. So very large in size. So typical file sizes go between 2 and 10 gigabytes per pipeline section. So the challenge here is how do we go from these very large files with millions of rows to then deliver some to the engineers that they can inspect and they can digest. So we collapse all that down first to point clouds, and then we collapse that even further down to free span flags. These are the outputs that you've seen on the screen with the red, amber, green. And the other thing before I progress, the fact that you've seen so much engineering background here, it's not by mistake, it's by design. So we composed the team to be exactly like that. So we have the engineering background, and Dan is the PO for that from the start. So that wouldn't be possible without that. So we have 3 models. You'll be pleased to know. The first one is machine learning. So that is a deep neural network. And the reason it works is because it can actually process these XYZ files directly. No gridding required. And that's a big point there for us. So sometimes what happens after the data is collected by the ROVs, this data gets gridded or voxelized. And when we do that, we destroy those inherent geometrical properties that we need for the models to work. So we had to actually really have a data-driven way of showing this to our users and to Dan that that data does not serve the model. So, and perhaps further on that, so these models capture all the geometric patterns you see on data. You don't need to start from scratch. So if you've seen how these models work, and if you imagine, for example, furniture in a kitchen, you'll see that you have things like points that then form lines, that might form the legs of a chair, and then you might actually see a chair being shown. This works the same way. So why lose all that and lose all those geometric patterns? So we didn't do that. Basically took a pre-trained model, we froze all the weights all the way down up to the last, and then we trained the last layer on our data, and that worked really well. So the idea with these models is that they're very good, they're too good, which means we can actually detect almost everything, but then also we have false positives to be quite high here on 38% false positive rate. So the way to counteract that is to bring physics to the play and to set manual rules. So these are physics-informed thresholds on height, gap, span length. So these are very fast, and they are very robust on kind of straightforward, if you want, seabed, and they have very low rates of false positives. So if one has very high false positives, the other one has very low, then the challenge was let's bring the two together. And that's our third model that blends those, gives you 89% coverage and 15% false positive rate. So if you really want to understand a bit more about PointNet+, so again, back in the day, standard CNNs required gridded images. This is completely opposite. We don't require that. So subsea bathymetry is ungridded. You can think of bathymetry, if you want, as almost like a strip of data that gives you like almost like a digital image of the seabed elevation. That's how it looks. And you see that in the image that it's not a surprise really that we are able to detect those gaps. To me, that looks the same type of gap that you'll detect between the legs of a chair, right? And the way that works, you start with the raw data, you run some clustering around the radii, and then you do different abstractions. And the way that works is that you look first at the points individually, but then you need to also back off from that view, almost like a zoom out, and build their hierarchical picture, and you start seeing things like lines that look like pipelines and seabed and so on. So the good news, performance across the 6 pipelines. The headline figure there, of course, is that we have captured 100% of the free spans that we tested across, and we tested that across different topologies, if you want. So pipeline 1, 100% coverage, very low false positive rate. This is because it's a sandy seabed, so quite easy. And actually, we could have just used physics to do that. So, but then if you go for a more kind of rocky environment, if you want, pipeline 5, you have high coverage, but high false positive rates. So this is where we get things like boulder proximity, lateral buckling, and so on. So the architecture, so this is what's happening right now in production. So we have the survey data lands in the landing zone. Databricks pipeline is automatically triggered. We run the model inference, so the two models plus the blended approach. This falls into an application database and goes into the NeMo front end. So, because we are using high performance computing, this actually runs in 30 minutes, which is awesome. So, perhaps one point, yeah, I have 15 seconds. It's the year-on-year consistency. So one of the real values here is on that, as Daniel was showing you those charts, because you might argue, what if we are not absolutely exact on the start and the end of the free span? Well, that doesn't quite matter so much, because we've proven we can do that for these free spans, and we are going to apply the same systematic approach year on year. And that is fundamentally different from having different human operators doing that job. Thank you.